In our next section here, we're going to look at problems that can occur during redistribution. We'll see two different types of loops that are related either to the metric or to the administrative distance, how to identify these potential looping problems, and then how to prevent them with different tools in the iOS. Now, first and foremost, the reason that we could have potential problems in redistribution with either traffic loops or actual routes, loops of the route information themselves, is that anytime we're doing redistribution between different protocols, we're causing a loss of the end-to-end route calculation and the loop prevention mechanisms that are normally built into that protocol. So, for example, with EIGRP, in the diffusing update algorithm, we're using that feasibility condition to figure out, is a destination that I'm learning a prefix from either closer to the destination or further away from the destination than I am. Now, when we compare this to OSPF's building of the graph for SPF, the two algorithms are not compatible, which means that when we do the redistribution, we're essentially potentially breaking those loop prevention mechanisms. So really, there's no way that we can prevent this since the protocols are having different formats. Ideally, in a real design, you would just try to get away from any redistribution points at all and simply run the same IGP end-to-end. So if I'm running EIGRP everywhere in my network or running OSPF everywhere in the network, then we can assume those protocols are going to build a loop-free topology to begin with. It's only when we pass the information between the protocols and then we have a loss of the entire reachability information, that's where the potential problems can occur. Now, we'll see on the command line that any design that is using just a single point of redistribution, so where one router is doing OSPF to RIP redistribution or doing RIP to EIGRP redistribution, in those type of cases, there is not a potential for route feedback or not a potential for a traffic loop. We'll see that the internal routing process is automatically going to control what routes are supposed to go from EIGRP to RIP, and then make sure those routes don't go from RIP back to EIGRP. The only potential problems we could have with redistribution is when there are multiple points that the different protocols are meeting. So if we're redistributing between OSPF and EIGRP, but there are two different routers that are doing mutual redistribution between EIGRP and OSPF, then we have a potential possible issue. Now, specifically, there's two cases where these routing loops can occur. Regardless of which type of routing loop it is, it's simply based on the fact that that some router in the network, or possibly multiple routers, is choosing the wrong information in order to get to the particular destination. So if my correct route is from RIP, but I'm choosing the incorrect route from OSPF, then we're going to have a loss of the traffic or feedback of the route itself. So there's two general cases that we can apply onto this. One of them is that the wrong path could be chosen based on the lower metric value when we're looking at two routes of the same protocol, or that the lower administrative distance is chosen when we're comparing two routes between different protocols. So, for example, if I have RIP and OSPF redistribution in two different points, the RIP domain could potentially get confused by choosing the wrong route that has a lower hop count versus the correct route that has a higher hop count. Or if I had multiple points of redistribution where I'm going from RIP to OSPF, OSPF to EIGRP, then EIGRP back to RIP, I could potentially have a case where one of the devices chooses the wrong prefix based on it choosing the lower distance of OSPF versus the higher distance of RIP, or the higher distance of external EIGRP. The problem with this, though, is that there are really no general rules that you can apply onto redistribution to make sure that you're going to avoid problems 100% of the time. So instead, what we really need to do is to figure out, based on this particular topology, where are the potential problems that we could run into. And this is going to be based on just us visually inspecting the network topology, looking at where the different redistribution points are, and being able to predict what are the potential problems. So ideally, before you get to the CCI lab exam, you should be able to look at any network topology and 100% of the time predict whether there is going to be a problem and whether that problem is related to metric-based loops or distance-based loops, or say, no, there's not going to be a problem because the routing process is going to figure it out itself. The issue usually with redistribution is that if there is a loop in the topology, a lot of times it's very time-consuming in order to figure out what the actual problem is and then figure out what the resolution is. So ideally, we would work in the opposite way to figure out, before even doing the redistribution, what is going to be the problem, and then fix the problem before it happens. But today we'll look at some example topologies where there are routing loops, and then see what are the different mechanisms we can use to identify where the problem is, and then ultimately figure out, depending on if the loop is based on the metric or based on the distance, what are the different implementations we can use in order to fix that particular problem. Now, we already talked about using the TCL shell with ICMP for doing ping scripting. Another tool we'll look at today is the debug IP routing output that's going to show us what particular protocol the routes are being learned from, what is the metric value, what is the administrative distance value, and then whether the route is being added or deleted over and over and over. So if we look at the debug IP routing output and we don't see that the topology is changing, then that case is less likely for a problem with redistribution versus some case where we see the route is added and deleted every 5 seconds. We'll also look at the IP route profile feature, which is used to collect statistics on the routing table and then tell us how many changes are happening over a certain period of time. So if we look at the result of the IP route profile statistics, and we see that within the past minute there's been 1,000 changes in the routing table, then that most likely means that the routing topology is not stable. Also, we'll look at outputs from traceroute, where this should be pretty self-explanatory. If I trace to a destination and I see the packets are bouncing back and forth between the same hops in the network, then that's a pretty good indication that there's some problem with the routing domain. So if my route points towards you and your route points back to me, then we're simply going to bounce the traffic back and forth until the IP time to live is exceeded. Now we'll see again that there's going to be two main categories of looping that we'll see today. Loops that are based on the metric and loops that are based on the distance. The reason that we need to separate the two of them is that there are fixes we can apply to metric-based loops that will not work for administrative distance-based loops. Now, the metric-based loops, these are the ones that are the easiest to prevent simply by filtering the routes at the different redistribution points. So this is mainly where the route tag filtering would be used, or we can manually specify access lists or prefix lists that lists what particular routes we do or do not want to redistribute. Technically, we could also use administrative distance here, but a lot of the times for a metric-based loops, a route tag filter is going to be the easiest and most efficient way to fix the problem. Now, with administrative distance-based loops, generally filtering at the redistribution point itself is not going to accomplish anything. So there's a fundamental difference between when the router is choosing two routes inside the same protocol and looking at the metric value versus looking at two routes between different protocols and looking at the one with the lower administrative distance. But again, for either of these, whether the loop is metric or distance-based, there's really no general rules that we can apply onto the topology. The key is that we need to look at the network diagram and essentially follow the route advertisement path on a hop-by-hop basis to predict for this particular router what interface is the routing update going to come in on, and if it is learning it from multiple interfaces and they're via the same protocol, which are we going to choose based on the metric? Or if it's coming in multiple interfaces through multiple protocols, which is it going to choose based on the lower administrative distance? So again, ultimately, once you are proficient with the route redistribution, you should be able to spend maybe 5 or 10 minutes just visually looking at the topology and tracing out the route path and figuring out where the issue is going to be before you actually do the implementation. So let's look back at our example topology here, where we have 3 different protocols in the network. We have OSPF, RIP, and EIGRP, where all 3 of them are terminating on router 4. So our ultimate goal here is to get reachability between all 3 of these domains, and we're going to be doing the redistribution on router 4. Now, we already looked at doing the redistribution between RIP and OSPF, and it did not look like there were any issues there. So RIP went into OSPF, OSPF went back into RIP. We did some basic tests by using the ping command and using the TCL scripting. Router 6 and switch 1, they were able to reach all of the destinations in the RIP domain. So next, let's look at on router 4, we need to add the EIGRP and RIP redistribution. And then lastly, we're going to go between EIGRP and OSPF. Now, as I mentioned before, for situations where there is only one meeting point of the routing protocol, it is nearly impossible to cause a routing loop, because the routing process itself is going to take care of any of these issues. Now, this type of topology would look like, let's say, between router 4 and BB3, we're running RIP. Then on the rest of the network, we are running OSPF. If router 4 is the only physical meeting point from the RIP domain to the OSPF domain, then we know immediately there's not going to be any problems with looping. We can simply redistribute RIP into OSPF, redistribute OSPF into RIP, and then let the routing process worry about it on its own. So internally, there is a mechanism that the routing process knows I should not take a route from OSPF and put it into the RIP database, then take it from the RIP database and put it back into OSPF. So we don't need to do any type of route tagging, any type of access list or prefixes filtering, or modify the administrative distance. Router 4 should automatically prevent this type of case. Now, where we are going to see problems is this type of example topology here, where there are multiple meeting points of the same protocol. So in this specific case, we have EIGRP and OSPF meeting on router 4. It's meeting on router 5, and then also on routers 1 and 3. So this then means anytime I take a route from OSPF and advertise it into EIGRP, it's going to be learned by the different routers through multiple protocols. So let's say on router 4, we're doing just one-way redistribution. We redistribute from RIP into OSPF, and we redistribute from RIP into EIGRP. So now I want to know visually on a hop-by-hop basis what exactly is going to happen when router 4 advertises these routes into OSPF, and then separately, what's going to happen when we advertise them into EIGRP. So first, let's look at the OSPF domain. So router 4 redistributes into OSPF. The route is going to go to router 6 and to router 1. Assuming that we are using all of the default values, the router should see these as OSPF E2 with a metric of 20. The administrative distance is going to be 110 as the default for OSPF for both the internal and the external routes. So now both routers 1 and 6 have this installed as an OSPF external type 2 route. Router 6 is going to pass this to switch 1. Switch 1 passes it to router 3 and to switch 3. So now all 5 of these routers, router 1, 3, 6, switch 1, and switch 3, should have the prefix that came from RIP installed as OSPF E2 with a distance of 110 and a metric of 20. Now router 4 is also redistributing these same prefixes into EIGRP. So from router 4, they go to router 5. Assuming that router 5 has EIGRP split horizon disabled on this frame relay interface, 5 should then send the route back to 1, to 3, to 2. 2 and 3 are going to exchange it over this point-to-point link. 1 and 3 are going to exchange it over that point-to-point link. And then router 5 is going to send this down to switch 2, and then over to switch 4. So now the potential problem areas are going to be anywhere in this topology where the routers are learning the routes multiple times. This specifically would be router 1, router 3, and router 5. Okay, I forgot to draw here. Router 5 is also going to learn this from OSPF, from router 4. Now from router 1's perspective, it's going to have two possible routes. The first of them is the OSPF E2 route with a metric of 20 and a distance of 110. It's also going to have the external EIGRP. This would be in the routing table as DEX with a distance of 170, and then the metric value of whatever the lowest bandwidth along the path is plus the cumulative delay. So in reality, it doesn't matter what the metric value is here because we're only comparing it against one possible EIGRP path. We're not comparing it against multiple ones. But the key point now is that when router 1 compares the EIGRP route to the OSPF route, which one is it going to choose and why? So again, when we're comparing the same longest match through multiple protocols, we're going to look at whichever one has the lower administrative distance. Since OSPF has a distance of 110 versus EIGRP's 170, it means the OSPF route is the one that gets installed in the routing table. Now, where this is going to be an issue is that for any device that is running EIGRP and is also learning the OSPF route, if the EIGRP route does not get installed in the routing table, what does that then imply about its advertisement? Because remember what I mentioned about RIP and EIGRP that's different from OSPF and BGP. With RIP and EIGRP, since they are distance vector protocols, they can only advertise what is actually installed in the routing table. Now, BGP and OSPF, since they have a larger view of the overall topology, they can advertise the route without actually having to install it. Specifically in this case, the problem that we're going to run into is that when the route is advertised from router 4 into the EIGRP domain and from router 4 into the OSPF domain, router 5 has two choices. It has the OSPF with a distance of 110, and it's going to have the EIGRP with a distance of 170. The OSPF route wins. This is the one that goes into the routing table. If the EIGRP route is then not installed, it means that router 5 won't be able to advertise it. So in this particular topology design, if we were to do mutual redistribution between RIP, OSPF, and EIGRP on router 4, we should see that everyone in the network is going to have reachability everywhere, with the exception of switch 2 and switch 4. Because when router 5 is learning the OSPF route versus the external EIGRP, it's going to choose the one with the lower distance, which is OSPF, which means that the EIGRP route doesn't get installed, which then means it cannot be advertised. So let's actually look at the result of this. Let's go to router 4, and we're going to do this redistribution. So to start on router 4, let's look at the show run section router to see what we have currently. Okay, between OSPF and RIP, we're already doing the redistribution. That's fine. Now, under the RIP process, I'll say redistribute EIGRP 1. Give it a seed metric. We'll say metric 1. Under the OSPF process, I want to redistribute my EIGRP process 1 and include the subnets. Then under EIGRP, I want to redistribute OSPF and RIP. Okay, under the process here, I'm going to specify what the default metric is. So let's say bandwidth in kilobits per second, we'll say 100,000. So that's 100 megabits per second. Delay in tens of microseconds, if we say 100, that means 1,000 microseconds. 255 is 100% reliable. The load of 1 means the minimum load. Then we'll say an MTU of 1,500. Now the load, reliability, and MTU, technically these values don't even matter unless you have your metric weightings set in a way that the load and the reliability are going to be included. The MTU is only used as a tiebreaker if you have multiple equal routes, where most of the time the effective MTU of the network is going to be 1,500 or less. But otherwise, it's really only going to matter what is the minimum bandwidth along the path, and then what is the cumulative delay. So now when I redistribute OSPF1 and redistribute RIP, I should see that both of these source protocols are then getting the same seed metric. Just like I verified previously with RIP and OSPF, we would be able to look at the local EIGRP process, look at the topology, and see are the RIP routes and the OSPF routes actually getting redistributed. So we can see it says that the 146 network, which is our connected route for OSPF, that's getting redistributed. These 30 and 31 networks, these are the ones that were coming from RIP. So the RIP to EIGRP redistribution is working. If we keep going, we see the VLAN 7 interface from switch 1. And switch 1 was part of the OSPF process. So that's telling us that the OSPF to EIGRP redistribution is working. So as long as the metric value is specified, again, it doesn't matter what it is as long as it's there, and we have the correct process numbers, then the redistribution should be accomplished locally. Now you can run into some cases where the routing process gets hung, and some prefixes that should get advertised don't actually get into the database. The way that you can fix this is simply by clearing the routing table. So if I say clear IP route star on router 4, that's going to remove all routes from the routing information base, which is the routing table. They're going to get repopulated from the source routing protocols and then repopulate the Ceph table. Problem is, in production, when you do this, you're going to end up dropping packets while you're temporarily repopulating the table. So for our purposes, for the lab, it's not going to be an issue, but you do need to be aware of this in your actual production designs. So now on the rest of the topology, let's look at what's the end result of this redistribution. If we were to go to switch 3, ideally we should see the routes coming from RIP, which were the 30 networks, that 204 network, and then also stuff that's originating from OSPF. So let's say the VLAN 10 interface is switch 4, which is 155.28.10.0/24. So on switch 3, if we look at the show IP route OSPF, we see we have a bunch of E2 routes. Some of them are related to the routes coming from the RIP process originally. Some of them are coming from EIGRP. Now, if I wanted to give some more visibility as to where did the routes actually come from, I could go to router 4 and say, under the OSPF process, when I redistribute EIGRP, I'll set the metric type to 1. Okay, and also include subnets. But when I'm redistributing RIP subnets, the default metric type is 2. So now when I look at the result of the routing table from the OSPF domain's perspective, it gives me a little bit more visibility as to where did the route come from to begin with. Now again, it's not really going to matter in this particular topology what the route type is, because there's only one physical path that we can use in order to get there. So whether router 4 is advertising an E1 route or an E2 route, it's not really going to matter because we have to go through router 4. But now it's just showing me that these particular prefixes, the E1s, those are the ones that came from EIGRP. The E2 routes, those are the ones that came from the RIP domain. So now on switch 3, let's do some basic tests. We'll ping 30.0.0.1. Okay, this tells me I can reach from OSPF to the RIP domain. Let's try OSPF to EIGRP. We'll try the 150.28.10.10. This is the loopback 0 interface of switch 4, which I do not have reachability to. So now this is telling me there's something wrong in the OSPF to EIGRP redistribution process. I don't necessarily know what, I just know that I don't have end-to-end connectivity. Now the next thing I may want to look at here is the traceroute output to figure out how far can I actually get into the network before the packets begin to get lost. So now if I trace to 150.28.10.10, this is going to tell me on the outbound path who has a route to get to 150.28.10.10. Then on the inbound return, who has a route to get back to me. Now if we compare this output here of the 4 hops to the diagram, from switch 3's perspective, we are able to send packets to switch 1. From switch 1, they're going to router 6, then to router 4, then to router 5. So to router 6, to router 4. Then the link it's using between 4 and 5 is the frame relay. So it's going down into the EIGRP domain. From here, now the packets are getting lost. So this tells me that somewhere behind router 5, so somewhere in that direction, either router 5 does not have a route to the destination, or the next hop doesn't have a route back. Now again, this is assuming that we're not doing any filtering in the network. If someone is filtering out UDP packets or ICMP unreachables, then the trace route is not going to be a good indication of this. But assuming we don't have any type of application layer filtering, then trace route is going to be a good indication of what the routing table actually has. So now let's look at switch 2 and switch 4 and see what is their view of the topology. On switch 2, let's look at the show IP route. And we should be learning both internal and external EIGRP, which from the look of the routing table, we can tell that there is a problem here. So I'm learning my internal EIGRP routes, but I don't have any external EIGRP routes that are being learned from router 5. Now notice the prefixes that switch 2 does have reachability to. This would be, let's say, 155.28.13.1 or 23.2. These particular prefixes are ones that are natively inside the EIGRP domain already. Now, even though EIGRP is being redistributed into OSPF, since the internal EIGRP routes are a distance of 90 and OSPF is a distance of 110, it shouldn't really matter that I have the same overlapping routes in the OSPF database as I do in internal EIGRP. So we'll see for most cases between OSPF and EIGRP, the protocols are pretty much going to take care of this on their own, what they should or should not redistribute, and what they should or should not install in the routing table. But we can see what the problem is now on switch 2 we don't have any of the external routes. Both the routes that should be coming from the RIP domain and the ones that should be coming from the OSPF domain. So let's go one hop closer to the source and look at what does router 5 say about these prefixes. So router 5 should be learning them from OSPF via router 4 and from EIGRP via router 4. Let's look at the show IP route. So notice in the routing table we have internal EIGRP, we have both internal and external OSPF, but we don't have any external EIGRP. So now I probably want to know, is router 5 even learning these external routes to begin with? Because remember, with EIGRP, what's in the routing table doesn't necessarily have to match up with what's in the EIGRP topology. We can have routes in the topology that don't make it to the routing table because of other prefixes that are taking their place. So on router 5, if we look at the show IP EIGRP topology, we can see that a bunch of these prefixes say that the feasible distance is inaccessible. What this essentially means is that router 5 is learning whatever this prefix is, but for some reason it's not getting installed in the routing table. And the reason why in this particular case is that OSPF has a lower administrative distance. So even though we're learning the prefix from router 4, if we were to look at the show IP EIGRP topology for that particular route, we have valid information about the prefix. It says the originating router is router 4. The minimum bandwidth is T1. The total delay, 21,000 microseconds. The reliability, the load, the MTU. Normally, the metric value should be 2.1 million. But it says our feasible distance is actually the infinite value. So when we see a difference between this value here, the feasible distance, and what the actual metric we've calculated through the neighbor, this means that we're learning the route from some other protocol that is stopping the EIGRP route from being installed. Now, since we're not installing the route as EIGRP, it then implies that we cannot advertise the route through EIGRP. So if we look at the routing table and say show IP route for 155.28.146.0, the source protocol is not EIGRP. The source protocol is OSPF. And since OSPF distance is lower than external EIGRP, means the EIGRP route is not getting installed, which means it's not getting advertised. Now, we could actually check this for every prefix in the network. What essentially we would have to do is go to all of the routers and collect all the addresses they have assigned on their links. And then we could use that to put together a TCL script. Now, I have an example of this already set up here. And let me pull up the actual document here. And I have a little bit of a variation of the script written here, where the script is inside a procedure. The reason I'm doing this is that once I define the variable, and this is the list of all the addresses in the network, once I run through this for loop, the variable basically is only temporary in that particular scope. So by defining a procedure, I can run the script more than once without having to redefine what are all of the addresses. Now, additionally, I have some other logic at the end that instead of showing all of the results for the output, it's basically going to give me two return codes. It's going to say either it's okay or the address is unreachable. And the way it's doing this is by looking at the result of the ping and then looking for three exclamations in a row. So if I'm sending 5 packets with a timeout of 1, ideally I should be able to get at least 3 responses in a row. That's going to be a fairly good indication of whether the reachability is actually there. Now, something like this, within the scope of the lab exam, you probably wouldn't want to write a script like this unless you're really good at programming syntax to begin with. Okay, but I'm going to use this for the rest of our examples, just so we can quickly tell what prefixes we do or do not have reachability to. Now, also, I'm only listing 30.0.0.1. I'm not listing all of the routes in the RIP domain. The reason why is that if I have reachability to 1, I can assume I can have reachability to all of them, because in this topology, these are basically just loopback addresses on BB3. So let's actually try this out. Let's go to router 1. Start the TCL shell. So I have the full list of addresses there. Now you can see it's going through the pings for all of them. So from router 1's perspective, it does not have any reachability problems. If we were to do the same thing from router 2, and let's actually test this from all of them. Okay, so I'll start the TCL shell on all the routers, and I'm pasting the same script in. On the switches here, for these 3560s, these are running 12.246 SE. So pretty much anything around this release should support TCL. Some of the lower level platforms like the 2950s, the 3550s, those don't support TCL. We'll look at in a little bit what are some workarounds we can do if you have a platform that doesn't run TCL, a different type of scripting logic you can use in the Catalyst iOS. But in the case of Switch 1 and Switch 2, these devices do support TCL. Switch 3 and Switch 4 don't, because these are lower level platforms. These are 3550s. So you can see, even though it's pretty much the same version of code, one platform supports it, one does not. But from Switch 3 and Switch 4's perspective, if we look at the diagram, I can pretty much assume that if Switch 2 has reachability everywhere, then Switch 4 is going to as well, because there's really no difference between these two configuration-wise. Then likewise, if Switch 1 can reach everything, it's pretty likely that Switch 3 is going to as well, because there's no difference in the OSPF configurations. Okay, so let's look at the results of this. From router 1, it says I have reachability everywhere. That's fine. Router 2 says there's a bunch of stuff that's unreachable. If we look at some of these, it's the VLAN 146. So both on router 1, 4, and 6's links. Anything that's on switch 1, anything that's on switch 3, router 2 does not have reachability to this. So if we look at specifically in the topology where router 2 is, for all of the OSPF routes, router 2 would have to be learning them from what protocol? Would have to be learning it from EIGRP, because that's the only one that is running. So now this is a pretty good indication that there's something wrong on the EIGRP network. From router 1's perspective, we were able to reach everything, which means inside OSPF, inside EIGRP, and then this way to get to RIP. So this is kind of narrowing down for me where the problem is going to be located. So we know now what the particular issue is. That router 5 is receiving the OSPF route and the EIGRP route. We have the OSPF distance of 110 versus EIGRP's 170. This means that the EIGRP route is not installed in the table, and then it cannot be advertised. So how can we fix this now? Now, ultimately, the fix for these loops is going to depend on why did the problem happen in the first place. So in the case of a metric-based loop, we generally can do some sort of filter that is going to delete the route that was chosen based on the wrong metric. But anything that is to do with the administrative distance, basically the only fix that we could have would be to change the administrative distance. Now there's some very few minor exceptions to this. We'll show one example here on router 5, but for the vast majority of cases, if the problem is because of administrative distance, you're going to have to change the distance to fix it. If the problem is based on the metric, it gives you more options as to exactly what you can use. But we know here specifically our problem is that router 5 is choosing the wrong route based on the distance, which is preventing it from having reachability to, or preventing it from advertising other portions of the network. So to fix this then, we're going to have to do what? We're going to have to change the distance on 5. So if we can change the distance in some way that the EIGRP route is installed in the routing table, it should then mean that we can advertise the route. But in our current case now, where OSPF is being installed instead of EIGRP, means that EIGRP cannot be advertised. Now another key point here with the administrative distance is that the value is only locally significant. So if I were to change it on router 4, it's not going to affect router 5. If the distance problem is on router 5, I have to change it on router 5 in order to fix that. So we essentially have two different options. We could take OSPF's distance and raise it so it's larger than EIGRP's, or take EIGRP's distance and lower it so that it's less than OSPF. Doesn't really matter which one we do, it's going to have the same end result. The only time where this implementation is going to matter is if we're trying to change the distance on a per route basis. Where with EIGRP, we cannot change the distance of an external route on a per prefix basis. With OSPF or RIP or BGP, we can selectively change the administrative distance on both internal routes and external routes. So I can say for the route 1234, I'm going to set the distance to be 5. But for the route 5678, I'm going to set the distance to be 10. For EIGRP, that works for only internal routes, doesn't work for external routes. Which is really fine in this case because we don't need to match the individual prefixes. I basically just need to say that router 5 should not be installing anything through OSPF. Because anything that's installed via this link is immediately going to invalidate the EIGRP information that's coming over the alternate path. So let's fix this by lowering the distance on router 5. We're going to take the external EIGRP from 170 and we're going to drop it to anything lower than 110. So 109 or below. So let's go through the routing process. Router EIGRP 1. We'll say the distance. For EIGRP internal, we'll leave that as 90. For external, I'm going to set this to be 109. So it's at least one lower than OSPF. I could set it to anything lower than that, just as long as it's no larger than 109. Now when I clear the routing table, then show IP route, we should now see the change that the external EIGRP routes are now being installed with a distance of 109 as opposed to the OSPF externals. Since these are now being installed in the routing table, it then applies that these routes should be able to be advertised. So now if we were to go to switch 2 and look at the routing table, show IP route EIGRP, we see now we have the external routes installed. So I can now rerun my ping script procedure and test reachability to the internal EIGRP routes, and then any of the external EIGRP routes, the ones that came from the RIP process or from OSPF. So now it's telling me from switch 2's perspective, basically I have reachability to everything with the exception of just one link. That is the link that is directly connected between router 5 and router 4. But from switch 2, I am able to reach the addresses on switch 1. I'm also able to reach the addresses on switch 3. If we were to look at a trace route, let's say to 155.28.9.9, which is switch 3, says the packets are going to 5, to 4, to 6, to switch 1, then to switch 3. So it's going to 5, to 4 over the frame relay, because now we're choosing the EIGRP route over the OSPF route. Then from 4 to 6, 6 to switch 1, and then switch 1 to switch 3. So it looks like now the vast majority of problems have been solved here, with the exception of just that one link, the link between router 4 and router 5. So even with the distance change on router 5, why did that not solve our problem with having reachability to that serial link directly between between 4 and 5? Let's take a look at what router 4 and router 5 says. So I first want to know, on router 4, did this prefix actually get advertised into EIGRP? If I look at the show IP EIGRP interfaces, that link, the frame relay, actually I want to look at, not that, I want to look at the show IP OSPF interface brief. Okay, interface serial 0/1/0, that's running OSPF area 0. That's the link that's connecting over to router 5. Since I am redistributing OSPF into EIGRP, it should imply that any routes installed as EIGRP plus any connected links, actually, excuse me, we're going the other way. We're going OSPF to EIGRP, means any routes installed in the table as OSPF plus any connected links running OSPF, that's what should be redistributed into the EIGRP topology. So if I look at the show IP EIGRP topology for 155.28.45.0/24, I want to know, did router 4 actually do the redistribution for this? Which it did. It says the next hop is 0000 from redistributed. This basically means that I am doing the origination. Okay, originating router is 150.28.4.4. This system, it means that's my router ID. Now, router 4 is adjacent with router 5 via EIGRP, so this prefix should be advertised in an EIGRP update message. If we look at router 5 and look at the same exact output, router 5 says, I am learning it. I am learning it from router 4. My metric normally would be 2.1 million. But the feasible distance value there is the infinite one. So why in this case would router 5 not install this route that it's learning from EIGRP? So let's look at what is router 5 installing it as. If we show IP route 155.28.45.0, this is a connected link. The administrative distance of connected links is always 0, and there's no way to change that. So the router is always going to prefer its connected interface over any dynamically learned route about that. So this now means, even though I'm learning it through EIGRP, with the modified distance of 109. 109 is still higher than the connected distance of 0. So it means I cannot install the route as EIGRP and I cannot advertise it. Now the issue we're going to run into here is that we can't change the distance of a connected route. So if router 5 is going to be advertising this prefix, what does it imply we have to do? So router 5 is only going to advertise this link to switch to in what case? If router 5 is locally originating it. So if router 5 were to do the redistribution, we would never see this problem to begin with, because there's no issue with taking the routes from the routing table as OSPF and then originating them myself as EIGRP. The only problem in this topology is that router 4 is doing the redistribution, so 5 is learning them through EIGRP with the higher distance than the OSPF routes, which means the EIGRP cannot get installed. Since it's not installed, it means that we're not advertising it. Switch 2 is never going to learn those routes. We tried to fix this by setting the EIGRP distance to 109 and left OSPF as default for 110. And that's going to be fine for the dynamically learned routes, but it's not going to affect our connected interface. So really the only solution for this would be to go to router 5 and then under the EIGRP process either do redistribute connected or just have a network statement that is matching that particular link. So if I say redistribute connected and then set the metric value, let's say, doesn't matter what it is, I'll just use all ones. Now on router 5, when I look at the topology, notice the change here. It now says this is coming from me as redistribute connected. So if we now look at the result of this on switch 2, we say show IP route 155.28.45.0. We see now the route is learned through EIGRP, which means then we should be able to reach it. So in this particular example, we don't necessarily have a routing loop per se. It's simply based on the advertisement rules of EIGRP. We're not allowed to continue to advertise a route that is not actually installed through that protocol. If we were to change the EIGRP domain with RIP, we would still see the same problem here. Because RIP has a distance of 120, where OSPF has a distance of 110. It means that when router 5 were to learn the RIP routes and the equal matches via OSPF, we would choose the 110 through OSPF, which means we would not advertise the routes out any of our interfaces running RIP. Now, if this was swapped around, though, on the point-to-point link between router 4 and 5, if this was EIGRP, and then down here this was OSPF, then we're not going to have the problem. Because from OSPF's perspective, it doesn't care if the route is installed in the routing table. It says that everyone who's in the link state area has to have the identical copy of the database. So the LSA flooding is independent of the path selection. Whereas with EIGRP and RIP, the path selection and the advertisements map on a one-to-one basis. So during path selection, if I say that some route is invalid, it means I cannot advertise it.